Alright, we're looking for a way to get nitrogen fluorine to both have 8 valence electrons. Nitrogen has 5 valence electrons to start with. In the valence level, nitrogen has 2 electrons in the S sublevel, represented by these 2 elements, and 1, 2, 3 electrons in the P sublevel, represented by these. And this whole set of electrons is in the valence level. So that's a total of 5 electrons. 2 and 3 makes 5. Fluorine, by the same token, then has 7 electrons. 2 in the S sublevel, 5 in the P sublevel of the second primary energy level. The highest primary energy level for any element is its valence level. That's a total of 7. 1, 2, 3, 4, 5, 6, and 7. We want to try and share electrons in such a way that both elements have all the electrons that they can fit into that valence level, which is 8, okay, most of the time. So I can share 2 electrons, say these 2 between nitrogen and fluorine, and because fluorine started with 7, it now shares 1, it has 8. This fluorine is now where it needs to be. But the nitrogen started with 5 and now has 6. It needs 2 more electrons. So we're going to put another fluorine in here. 1, 2, 3, 4, 5, 6, 7 electrons, and share these 2. Well, that takes care of that fluorine. Fluorine has 7. It's sharing 1. It now has 8. Nitrogen's, when we started with this stage anyway, had 6. Now it has 7. So we need another fluorine. So we're going to share these 2. Now this gives every element in our illustration here anyway, every atom, every element symbol, the 8 electrons it wants. Now that's not the end of the story. That's sort of the beginning of the story. So we've got to finish our comic book here, where we now are going to show that fluorine is sharing electrons with nitrogen. We do that by squeezing those shared electrons in this sharing arrangement drawing, squeezing them together to make what's called the Lewis dot formula. Squeeze these 2 together here so they're like that. And then we put the extra electrons all the way around. Okay? Just to reiterate the terminology, this is a shared pair, this is a lone pair. Shared pair, lone pair. Shared pair, lone pair. If it's shared between 2 atoms, it's a shared pair. It's kind of sitting out there by its own lonely self. It's a lone pair. Now you do sulfur and iodine. I shouldn't have capitalized iodine. I'm going to change that to a lowercase I here. Sulfur and iodine. Alright, sulfur has how many valence electrons? 6 valence electrons. 1, 2, 3, 4, 5, 6. How many valence electrons does iodine have? 7. 1, 2, 3, 4, 5, 6, 7. Okay, so sulfur and iodine can share these two electrons, and just to help you, if you haven't figured it out already, you don't break up pairs. You don't break up pairs unless you absolutely have to, and we won't get to that actually in here. So we want to look for the lone single electrons to share, okay? So now iodine had 7, it's sharing 1, now iodine has 8. Sulfur had 6 electrons, it's sharing 1, it now has 7, so sulfur needs another one, and it's going to get another electron to share from iodine. So I need another iodine here. 1, 2, 3, 4, 5, 6, 7. Excuse me. And then we're going to share these 2 electrons here. Now this iodine, which started with 7, shares 1, it has 8. Sulfur, which originally had 6, shared 1, got 7, shared another one, it has 8. Now both of these element symbols or atoms are more stable. And we can draw the actual Lewis dot formula. So here's iodine sharing these 2 electrons with sulfur. We squeeze them together like this, like an over and under shotgun. So I am recording now, and anybody listening to this video, we're in South Carolina. People know about guns. So down here, we're going to squeeze these 2 electrons, and we get a double barrel shotgun. Okay. All right. And we have to put all of our lone pairs around the whole structure. All right. You did yours different? You know what? There's absolutely nothing wrong with that. That's a very good point. As long as you have 2 sets of shared electrons between the sulfur and the iodines, the side you have the iodines on doesn't matter so much. Yeah, that's perfectly okay. Okay? Now I hope nobody listening to the video is offended by the over and under and double barrel thing. You can think of that as a colon, and this is what, two periods or something. I don't know. A colon? You know, like 2 dots, one on top of the other, a colon in a sentence? Yeah, not the one that's in your belly. Okay, all right. All right, one more practice problem. Phosphorus and bromine. Shh. Do this, please. Phosphorus and bromine. Phosphorus and bromine. Less talking, more working. So people listening to this video know we're in South Carolina because I say talking instead of talking. Okay, so here's the correct, quiet please, thank you. Here's the correct formula then for phosphorus and bromine. If we were going to name this 1 phosphorus, 3 bromines, phosphorus tribromide. Okay? If we were going to name this, what would we name it? Sodium diiodide. Remember in Unit 2 when we were figuring out the pattern of electronegativity? Highest electronegativity is here with fluorine. The lowest was down here around cesium. Okay? The closer you get to fluorine, the more electronegative an element is. So you always list that more electronegative element last. Okay? So iodine is more electronegative than generally sulfur, although you could go either way. All right. Nitrogen or fluorine is more electronegative than nitrogen, so this would be, what would you call this? Nitrogen trifluoride. Good. Okay, now, one more thing about terminology before we can go to the next subject. Okay? These, when you have two electrons share between two atoms, when you have two electrons share between two atoms like this, that's called a single bond. Two electrons share between two atoms is called a single bond. So we've got single bonds here, and here, and here in this drawing. Okay? You got that? Here we've got a single bond there and there. Got single bonds down here, 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 and here. All right? So, single bonds don't solve all the problems for the way that atoms actually bond together. What is it you guys are breathing right now? And oxygen is the primary ingredient that we breathe in and use. It's not the primary thing in the air. The largest concentration of gas in the air is nitrogen. But let's start with oxygen, O2. How many electron dots does an oxygen atom have? 6. 1, 2, 3, 4, 1 on each of the four sides. Pair up as needed. 5, 6.
Is this an example?
This is an example. So here's another oxygen, because I need 2 of them. 1, 2, 3, 4, 5, 6. I need to be able to put both these together in a way so that we have 8 valence electrons. How's that? How about we share these 2, and then we share these 2.
Yeah, you will.
So, okay. But we got to when we draw the drawing, any shared electrons have to be squeezed between the symbols, right? That's our rule. So here's one oxygen, here's the other oxygen, and when I squeeze 4 electrons in between, we do it like that. Okay? The unshared pairs are then put around the outsides. Okay? So now we have not 2 electrons that are shared between 2 atoms, but 4. It's called a double bond, yes. Because we're sharing 4 electrons. We're sharing 4 electrons between 2 atoms. Sharing 2 electrons is a single bond. Sharing 4 is a double bond. So I want you to stop a minute and think back. Give me your attention here, please. Think back to orbital notation. Okay? Each orbital contains 2 electrons when it's full, right? We are filling up orbitals when we fill up or pair up these electrons. Okay? And that's what at least part of what makes these atoms more stable and cause them to do what they do. Okay, so by sharing electrons in these pairs like this, we fill up orbitals, as well as filling up valence levels. All right, now your turn. Nitrogen. Nitrogen. See if you can figure out how that goes together.